Now I want to discuss how to apply quadratic functions to real-world type problems. First thing we want to discuss is how the facing up or facing down parabola tells us about the values associated with the function. So if we have a parabola that faces up, one of these parabolas, we're going to have a minimum value at our vertex. And if we have a facing down parabola like this, then our vertex is going to form a maximum value. And what we're getting is for our maximum, the independent value is going to tell us when our maximum value is attained for our dependent value. So remember, the vertex has both the independent and the dependent values in it. So those are the applications of these. Now, one of the types of application problems that we will see is going to be a minimizing and maximizing of areas. So these problems take on a double type of feature. What we're going to be looking at is some formulas that we already know and creating an expression from one formula to plug into a second formula. So let's look at this example. I wish to fence a rectangular shaped paddock. A paddock is just a pasture or something that contains animals. So here's my rectangle, and I want to use 500 linear feet of fencing. Well, that's telling me about the perimeter of this paddock, that it can have 500 linear feet of fencing around it. And then it says, what are the dimensions, the length and the width? So we know that this is the length and this is the width, or vice versa, because remember, it really doesn't matter. To give the what are the dimensions of the largest such paddock I can create? So what we're looking for is the area of this paddock, where our length times our width is going to be equal to the maximum area. So in order to maximize that area, I have to use my constraints, which my constraints are based upon the perimeter of the fencing. So that perimeter is doing what we call a constraint on the area in order to maximize it. So we are first of all going to find out how we can associate the perimeter with the length and the width. So we're going to come down here and we're going to say, okay, well, we know that perimeter is 2 times the length plus 2 times the width, and that has to be equal to 500 feet. So the next thing that we're going to do from there is that we're going to solve that perimeter in terms of the width. So I'm following along the step process over here. So that was step number 1. So step number 2 is going to solve the perimeter for the width. So in order to solve 2L plus 2W for the width, I'm going to put this in color so I know that that's what I'm interested in, and I'm going to work on solving for that variable. So the first thing that I'm going to do is I'm going to get rid of the 2L by subtracting it, which is going to give me the equation 2W is equal to 500 minus 2 times the length. And now the next thing that I want to do is I want to solve for W. So in order to solve for W, I'm going to have to divide both sides by 2. Now remember, that's dividing the entire thing. So this is going to give me that my W is equal to 500 divided by 2, or 250, minus 2L divided by 2, which is L. So there's my expression for the width. Now I'm going to take this expression for the width and I'm going to substitute it in to the area formula. So I know that area is equal to the length times the width. So I'm going to form an equation only in length here. So I know my area, which is now a function of the length, is equal to L times 250 minus L. And that's my area. Now this one, I want to expand it out so that I can see a quadratic equation out of that. So my area as a function of the length is equal to 250 times L minus L squared. Now another way of looking at this is that this is negative L squared plus 250 L. So at that point in time, I want to find out what the value of the length is that maximizes the area. So to maximize the area, that's what I need to do, is I need to find the vertex of this. So in order to find the vertex, to find the vertex, I have to use the formula for the vertex that the x is equal to minus b all over 2a. So this is going to be the opposite of whatever b is, and remember that b is this value right here that's multiplied by L. So my b is 250, and that's divided by 2 times whatever my a value is, and my a value is this value right here. So my a is a negative 1. And now I'm going to simplify that. So I'll get a negative divided by a negative, which is going to give me a positive value. So we have 250 divided by 2, which is going to give me 125. So now I know what the x-coordinate is. Now I need to find the y-coordinate, which is simply plugging in to the formula here. So I have 125 times 250 minus 125, and I find out the value there. So this is going to look like 125 times 125, and that's going to give me, is that right? Let's see. We have, let me check that on a calculator. So 125 times 125 is 15625. So now what I have is my x and my y coordinates, or this, remember, my x is my length and my y is my a of L, which means that's the area of the fencing required. So I want to find the value of the independent, and then the next step here is to find the area of the finding the area, and I don't actually have to multiply the length times the width because I already know what the length is and I already know what the area is. So this is my area, and this is step number 6 without actually doing the work there. And this one, the value of the independence, is part of step 5 because that's my length, and then I can find out what my width is. My width is also 125 because it's 250 minus that. And these, of course, are some number of units, and these were feet units. and feet units. And then when I have an area, that's feet and, of course, squared. So, get a different color entirely here to highlight. So there's my width and there's my length. Those are my dimensions that were requested, and the 15,625 feet squared, that's the area. So that's step 6. All right, now that completes the first problem. So we're going to go on in the next video and we'll complete the next problem, which is another problem, but this one is a minimization problem. So we just saw a maximum problem, and as you saw that maximum problem, I do want to point out that notice the equation here that we got. It had the negative, right? So we know that this is going to be a problem where we have the vertex right at the top, so we're finding a maximum. And see, that's how you know whether you're maximizing or minimizing. If you're trying to find a maximum, you better end up with an equation, a quadratic equation, that has this key feature of having the negative as the numeric coefficient of the squared variable.